Okay, so now that we kind of understand how elements combine, it became an issue and of interest to scientists to figure out, all right, if I have so much starting material and I put those two things together, how much stuff will I make? That seems like a pretty logical question. And here's one of the big issues that scientists kept running into, is that when atoms combined, they don't do so based on their mass. So, like if you had 3 grams of one reactant and 6 grams of the other, you're not necessarily going to get 9 grams of the one specific product that you want. Instead, atoms combine based on the specific ratio of atoms. So here's a little formula of that. If you take some CH4, which is this stuff right here, it's also known as methane or natural gas, and you combine that with oxygen gas, you're going to get two things, carbon dioxide and water. So the idea is, well, how much of those two things am I going to get? How much of the two things am I going to need to start with in order to produce the required amount of this or of this? All right? So those were the underlying questions that we faced. So in order to do this, in order to kind of predict the amount of stuff that we're going to make in a reaction, we must be able to figure out kind of how many atoms are in the samples of reactants if we're going to figure out how much stuff is being made. And that itself is a tremendous question. How many atoms are in the samples? Well, we know that samples are incredibly small. So how do we count atoms? Obviously, we can't do so individually. There are more atoms in a sample of 12 grams of carbon than there are grains of sand on this planet. So think about that for a second. You're not going to be able to individually count atoms. You're going to be counting for a really long time, and atoms are really small, so you're probably going to screw up. So one way we can do this is to use a system called counting by weighing. Let me give you an example of counting by weighing. Let's say you've got a bin. It was just Halloween, so we'll go with candy theme. Let's say you've got a bin of M&Ms, right? You get a bin of M&Ms, and I'm going to use my little red to make the M&M. Here's my little bin of M&Ms. Okay, and I asked you, okay, I want to know how many M&Ms are in there. Now you could pour out M&Ms. M&Ms aren't that small, and you could individually count them. Okay, you can count them all. Or let's say you have a scale next to you, which in chemistry labs is usually the case. You could take one of those M&Ms, boop, and you could put it on the scale, and you could get its mass. Doot, doot. All right, let's see what that comes out to. 1 gram. Yay. All right. And then you could take that entire bin. Let's say you knew the mass of the bin, and you teared that off, so you're not massing the bin now. You're just massing the stuff inside of the bin. And then the bin said, oh, that's 500 grams. Okay. Well, if you know one individual M&M has a mass of 1 gram, and you know the entire bin has a mass of 500 grams, I might ask the simple question, what would be the mass, or what would be the total number of M&Ms in the bin? 500, right? That'd be 500 M&Ms. It's a lot of M&Ms. But M&Ms are tasty, so that's a good thing. Right? So this works if and only if the sizes of each one of those atoms, or in this case M&Ms, is exactly the same. And that's one of the postulates that Dalton kind of brought up in his theory, that, yeah, it's true. Each one of the atoms inside of the bin, or each one of the atoms that make up a sample of hydrogen, are exactly the same. So we're kind of living off of that hypothesis. Okay? So we can do this same idea with atoms. But in order for this to work, we needed to know the mass of one piece of each candy. Remember what I did? I took a single piece of candy, single piece of M&M out, and I put it on the scale, and I weighed it. Well, you can't exactly take a single atom of hydrogen or oxygen and pluck it out of the air and place it on a scale and get its mass. I mean, we can do that nowadays, but you got to remember, people, this was happening back in, like, I don't know, 1700s. So they didn't have that technology. So for atoms, this means a single atom. It's not possible at this time. And it's actually still really, really hard to do if we want to get the mass of a single atom by putting it on a scale, quote unquote. So, all right, how do we do this? If we're going to count by weighing, we need to know some information, some more information. So Avogadro looked to his famous law for answers, and his law, remember, said this: equal volume of gases had equal numbers of particles, as long as those gases were at identical conditions. So let's look at 3 different gases. Let's look at hydrogen. Hydrogen. And let's look at nitrogen. And let's look at oxygen. All right, now let's go ahead and assume that each one of these samples has the same volume, same exact volume. So let's just pick a number out of thin air. Let's just say 22.4 liters. Okay, crazy number to pick, but you'll understand why I picked it in a later chapter. Let's just pick that one for right now. Okay, 22.4 liters. So each one of these boxes, 22.4 liters, same pressure, same temperature. So Avogadro says same number of particles in each one of these boxes. I don't know, however many that is, a bajillion, whatever a bajillion is. He doesn't really care. So then he goes on and he says, okay, what's the mass of each one of those boxes? So he takes the mass of the box of hydrogen and he sets it on a scale, and he gets 1 gram. Actually, he gets 2.02 grams. Okay, and then nitrogen sets that on the scale, and he gets 28.01 grams. Oh, so what's that tell you about the size of a nitrogen atom as compared to a hydrogen atom? It's bigger. Oh my goodness, earth-shattering. Okay, so then he does the same thing for oxygen. Here we go. Okay, 32 is what he gets on his scale. Super. Okay, now, here's the cool thing. He knows that as long as he knows like the masses, the relative masses of the atoms, he doesn't really need to know the masses of each individual atom. So he says, okay, well, hydrogen's like the smallest thing. It's the smallest of all the things that I've ever measured. So let's call that like the standard. Let's make that our standard. So, I'm just going to erase these for a second. So he takes that and he puts that over 2.02 grams. He says, okay, that's going to be 1. Okay, I'm going to compare everything to hydrogen. All right, and he does the same thing for nitrogen. He's got, remember nitrogen, when he put it on the scale, is 28.02, and then, so he divides that by 2.02. Remember, he's comparing everything to hydrogen, and that comes out to about 14. Okay, so hydrogen is 1, nitrogen is 14. He does the same for the oxygen, and that comes out to 16. Okay, so 1, 14, and 16. 1, 14, and 16. So he knows that the nitrogen atom is 14 times bigger than the hydrogen atom, and the oxygen atom is 16 times bigger than the hydrogen atom. So he actually gives these things labels. He says, well, they're not really grams, because if you look in the math, the grams cancel out. So let's call this, I don't know, let's call this an AMU, atomic mass unit. Sounds very technical. And there we go. We now know the masses of a certain sample of each one of the gases. Okay, the sample of each one of the gases. And that's kind of cool. So we found out different masses for each of the gases involved. Okay, so like we said, our initial question before with the M&Ms is how do we know the mass of like a single M&M? Well, we put that on a scale. We don't need to know the mass of a single hydrogen atom. We just need to know the mass of a relative sample. So we now know that hydrogen has relative mass of 1, where nitrogen is 14 times bigger, and oxygen is 16 times bigger than that. So that's what we will use to do our counting by weighing. Okay? So if you have a sample of oxygen gas that has a mass of, I don't know, 1,000 grams, and it was oxygen gas, you would know that that single initial sample had a mass of 16 grams. You divide it, and now you will know how much total amount, or the total number of particles are in that sample. Okay, so he needs to define something. He needs to say, okay, so what does this mean? If there's 1 AMU of this, and if there's, remember this was hydrogen, and this is nitrogen, 14 AMUs of this, and if this is oxygen, this is AMUs, this is 16 AMUs. So he knows from his law, he says that, okay, each one of those has the same exact number of particles. So, I don't know, that's just like a whole bunch of stuff. Let's call that a mole. And he spoke Latin, I think, and mole means lump of stuff. Okay? So in a mole, or a lump of stuff of hydrogen, there's 1 AMU. In a mole, or lump of stuff of nitrogen, there's 14 AMUs. In a mole, or lump of stuff of oxygen, there's 16 AMUs. And that's all he knows. And he knows that for a long, long time, and everybody else after him knows that for a long, long time. And it isn't until we do more advanced technology that we figure out that the number of atoms in every single one of these samples is exactly the same, based upon his law. And that number is actually a really big number. It is 6.0221 times 10 to the 23rd atoms that equals 1 mole, or 1 lump of stuff, as the Latins would say. Okay? All right, so lastly, we now know all this stuff for gases. That's super, but that only makes up like 4% of the periodic table. What about for the masses of non-gases? Well, here's what we know about non-gases. Like metals, they do a pretty good job of combining with oxygen. We saw this with the magnesium. Don't look at the bright light, right, on the right side of the page. Okay, so we saw that metals do a good job of combining with oxygen. So we can use this idea of percent composition in known relative mass of oxygen to find the relative mass of metals. I'm just going to go through a quick calculation here for you to show you how that is done. Let's say we have an original mass of magnesium of 60 grams. And let's say we burn that magnesium and oxygen, we take the sample, we put it on the scale, and we find out that the new mass, the new stuff that's produced, this white powdered stuff, has a new mass of 100 grams. Where did that extra 40 grams come from? Oxygen, because it combines with magnesium. So let's do a little ratio action here.
Can I have your attention, please?
Okay, so 40 grams. 40 grams of oxygen over 60 grams of magnesium. Now, what do we know about oxygen? We know its relative atomic mass is 16. We don't know that for magnesium, right? We don't know that. That's our X. So there you go. Cross, multiply, divide, do all your mathematical stuff, and you find out that the relative atomic mass for magnesium equals 24 AMUs. And check out your periodic tables. I don't know if you have one of those online or something. Hanging up in your bedroom, maybe a shower curtain that is a periodic table. I bet you find the number 24 associated with magnesium. All right, so that's all we need to know. It's important to say knowing the relative mass of elements is fine, because now we know how they're going to combine, in what number ratios, and how much they're going to combine with, and how much they're going to produce. There we go. That's your note.